Hi everyone, in this video I would like to cover problem number 16 on 2019 Purple Comet. This is a well written, a quality question written by those problem proposers at the Purple Comet, and this has to deal with permutation allowing repetition and one-to-one correspondence. All right, so let's just jump into the questions. I need to find the number of ordered triples of sets T1, T2, and T3. Basically, you need to use one-to-one correspondence for this one, such that each of T1, T2, and T3 is a subset of 1, 2, 3, 4. So my universal set is going to be 1, 2, 3, 4. So I got a universal set, U, where U stays as 1, 2, and 3, and 4. And I would like to read the questions, those three last conditions, such that T1 is actually staying in T2, or T3. T2 is going to stay inside T1, T3, and T3 is going to stay inside T1 or T2. All right, so we got three conditions, and let's suppose, or just assume that an element stays inside one of the sets, okay? So if an element stays in one of those sets without loss of generality, we're going to assume that it's going to stay inside T1, and if it stays right there, it needs to stay in, this implies that A stays in either T2, or maybe A stays in T3, or maybe A stays in T1 and T3 at the T2. So, T2 and T3 at the same time. Right, so here's what's happening. If A stays in T1 and A stays in T2, the second line is automatically just, satisfied. But at the same time, if it stays on T3, the third one is also satisfied. But at the same time, the last one satisfies all three altogether. Now, here's what's going to happen. And this is the reason why I call this as a permutation allowing repetition. Now, there's a T1, and there's T2, and there's T3. And imagine that A stays just in T1. So for instance, just think about apple bitten off twice, right? So if you think about this plate right here, this place, well, that little portion, if it contains any of those elements, let's say one goes inside there, then it's not part of T2, it's not part of T3. So basically none of those conditions are getting satisfied. But at the same time, so that's a problematic part. So I cannot place any of my elements inside those little, like the colored regions. But at the same time, since we've, assumed that it's going to be T1 with symmetric properties, I would say, I'm not able to place any of my elements in that, places, just T2. And at the same time, none of those, parts in T3 of that region will, none of those regions will contain any of those elements that we have. All right, so now if I place one of my elements and suppose I call this as number 1, well, it's going to be staying in T1 and T2. So I would say that will be this picture out here, this little small region out there. And if it stays in, T1 and T3, I would say it's just going to be marked out as that region too. And at the same time, if it's just a T1 and T2 and T3 all together, it's going to be the middle spot that you can see. And of course, we haven't thought about it, but if I just write down the fact that B stays in T2, then B can stay in T3. So I think I can come up with those fourth region. But what if none of those elements stays inside any of those T1, T2, and T3? That's still fine. We still have the last part, which is outside T1, T2, and T3, right? So in other words, we have 1, 2, 3, 4, 5 different plates where each of those elements can be placed. In other words, one can be placed in either circle 1, circle 2, circle 3, or circle 4, or circle 5. So there are 5 spots, right? So 5 spots for number 1, one element, and another element, we got 5 spots, and 5 spots, and 5 spots. So we get 5 to the power of 4. The answer becomes 625, and that shall be it.